Okay, let's start. Now I'm also recording, so you can hear me still. And you get the first page of this exercise sheet. Okay, fine. So let me go back to the exercise we started. We had that housing system, so we had the sensor. We had put it on a printed wiring board substrate. We used this with an adhesive. Here we have a flip chip attached to our printed wiring board. Here is this MEMS sensor with wafer level packaging, and now we also have seen the sequence of different fabrications, and so that was the overview in your exam. It will be important that you have the right order, and for these individual points you can you must give now more details. So the first thing was substrate fabrication, and we said we want a printed wiring board here. The second was produce a housing including a lead frame using pre-molded packaging technology. Then we have zero level or wafer level packaging. We have a heat sink, and what is important, we have also a flip chip bumping process. Then we have the flip chip soldering, and we will have assembly of the sensor element here. The substrate is mounted into the package. Then we must do wire bonding. We fill up with silicone, and finally we mount the lid and close it. And the very last step is to glue the whole thing to a heatsink. Okay, and now let's start with substrate fabrication. Printed wiring board. Fabrication. And how do we start here? We have one individual layer of this sheet material, and this individual layer has feed-throughs which are, for instance, copper. Of course, in the exam you cannot go into all of the details, but it is important that we know what is the first step. We have this single layer of epoxy glass. Then we must do metallization, and in order to short it up, it is a so-called semi-additive technology. So second is via. With semi-additive technology. Maybe you still wonder what this is. Semi-additive means we have additive processes and also subtractive processes. In the end, it is mainly a chemical metallization. or electroless. What is the next thing which is important in that process? We typically want to have a multi-layer, and that could, for instance, mean that we have another layer here, which has been processed in a similar way. And now, in between, we must put a so-called prepreg. What is a prepreg? Prepreg is a material which is not yet hardened completely. So these are the glass fibers. So that was one layer, and the second is we have a multi-layer. To that purpose, we stack several layers. And we have an intermediate layer of a prepreg. What is a prepreg? A prepreg is epoxy glass, only partly hardened. So that's the so-called B stage. Okay. Then we give pressure on it. So, pressure. What else do we need besides pressure? Yes, of course. In order to harden the epoxy, pressure okay. Are we finished then? What is your idea? What else do we need in the multi-layer? Of course, again, we need via holes here. And what will we do in order to get these vias? Yes, I would do so. So that would be then the vias in the multi-layer. So first drill. And how do we get the metallization? Yes. Okay, so that was 3, was 4, that was 5. Via metallization, like in above 2, like here. Yeah, so semi-additive process. What else do we need then? Do you have an idea? What do we have on a printed wiring? What do we have on a? Yes, that's good point. We have a solder resist mask. And we have a surface finish. Finish. So, okay. No, that was not good. Finish. Okay. So we are finished with the printed wiring board. Yeah. It can be much more complex, but I would say that's a simple way to do it. Of course, normal way. Yeah, go ahead.
Sorry, can I have one question? So, do we need to create some of the layer for the wiring for the wiring board later?
Yeah, that would be a good point. Of course, here when you do wire bond, here you could already say nickel gold plating. Yeah. For me, that was implicitly with surface finish, but of course, so what you shouldn't do is, yes, here to say I take tin as a surface finish and later on you want to wire bond on it. So that would be a small mistake, yes, but all of the things should be consistent. Okay, so the next step is the housing. So in fact, what we have in some way is we have some copper structure which is embedded let's say in some polymer structure. So that would be just a simplification. And how is it produced and what do we need for this? First of all, we must we have 3 parts we have to fabricate. And these parts are one, the lead frame. The second is we need a mold in order to mold this material into it, and only after that we can have the polymer part. So the lead frame, how is it produced? So typically we need a CAD, a design, then tools are fabricated, and these tools are especially for punching and also for bending. And then we can punch and bend the lead frame. So that's here we need some presses to do this. And finally we can again do the surface finish or of that lead frame So again, it could be nickel gold. For the mold, again we start with a CAD. We produce the mold by some mechanical machining. So that's some grinding, drilling, and so on. If that is finished, of course, the mold is installed in the molding machine, and in the next step is the injection molding. Here we place the lead frame in the mold. And what did we say? Which material do we have for the polymer? I think it was PA6 or something. Yes. So in that way, our housing was produced. Also, what is important is the wafer level packaging or wafer level hermeticity. Here we have several options. It is important. So here we will not go into the details of the semiconductor fabrication. So we can just say fabrication of the MEMS. Second is fabrication. For MEMS, what would be the typical technology we use here? No, it is not, because the CMOS technology is on the flip chip side. Here it is micro machining, and typically modern gyroscopes are produced using so-called surface micro machining. That means we typically have thin layers. The fabrication of lid, it is typically by bulk micromachining. For instance, deep etching with KOH or something like. And the last thing could be, for instance, then of course we need to heat out. Before we close a hermetic seal, why do we have to heat out? We must get rid of water. For instance, at 250 degrees centigrade for X hours in dry atmosphere. And the last is we can do a bonding process. There are many possibilities. For instance, eutectic bonding, gold silicon, and that is typically done at 420 degrees centigrade. Okay, in that way we have produced our lid here on our gyroscope. And here that would be the gold silicon bond line. Okay, in that way it has been accomplished. What else do we need in our process? The heat sink. So that's simple. I can put it on that page. What would be the material of the heat sink? Can you give me an idea? Yes. Good point. You can also use aluminum, but copper is better. So we make a CAD. We have a mechanical machining. Sometimes we can also use alternatively some extrusion. So the material is pressed into some kind of matrix under a high pressure. That is also possible. That's especially possible in materials when we have some endless structure, and in the end we saw just, let's say, some centimeters off from that structure. So here we can say or extrusion. So it's more done in aluminum. And finally, for the copper, we can again do some surface finish. For instance, electroplated with nickel. Okay. The next thing is something which should be new to you. But that's something you will also see in the lecture. That is a flip chip fabrication. Alternatively, you could have produced a surface mount device, for instance, a QFN chip scale package. On the other hand, we do not have to go into this because we have already exercised this several weeks ago. So we already went for this. So I would like to go to flip chip fabrication. What is flip chip? To make it short is we have a substrate, and on the substrate we have some landing sites, let's say 4. And of course we need some landing sites here on the chip. And now the question is, what do we have in between? Here we have our solder material. And here is the printed wiring board. And here is the silicon chip. But now a question, can you solder with a normal silicon chip? So to that purpose, let's have a look at the surface here. And now I only make space for 2 bumps. That's sufficient to show the principle. What is that what I have painted in blue here? What is it? And what is the green here? Can you tell me?
Is it the metallization layer on top of it, on the blue?
Yeah, what is the blue thing?
The blue are the aluminum bonding pads.
Yeah.
Green is the silicon
Okay.
for the isolation layer.
So here we have the passivation. Something like, for instance, such a material, and for the aluminum, we typically have, for instance, aluminum, silicon, copper. So, for instance, 1% silicon, 0.5% of copper. Now the question is, could we just solder to that aluminum with a normal SAC solder? Would it be possible or not? SAC is tin, silver, copper, normal tin alloy. Can we solder onto is it possible or not?
I would better know.
Definitely not. Because aluminum has a layer of aluminum oxide, and that is something which is not so good, and to that purpose we need a so-called underbump metallization, UBM, that is solderable. And for that purpose, we need it is good to use a semi-additive process. Again, what does it mean, semi-additive? That means we have some deposition and also some etching. Yeah. So the question now is, what do we need? A typical underbump metallization, it consists of titanium tungsten and of copper or nickel or copper plus nickel, and on that we typically have the SAC. And now, how can we produce it? And I will show you. First of all, we have the titungstem. Give it a special color. Because this titanium tungsten gives good adhesion. Also, when we use titungstem, this oxide layer of aluminum is not so important anymore, and it is also a diffusion barrier. So that titanium tungsten is sputtered. The next thing we do is we sputter also a thin layer of copper. And we do it in the same machine like we do the sputtering of the titungstem, so we do not get any intermediate oxide layers or so. So the adhesion is always best when we do it in one process, just changing the sputter target. So why do we need a continuous layer of copper? That is that makes the complete surface conductive, and in that way we can electroplate with copper. But that would not be a good idea when we put on copper here completely. So first we put on a photoresist. And what I'm already doing is that resist, that is typically some polymer. So we put on photoresist. And how do we get this structure in this photoresist? Can you just tell me one word that describes it sufficiently? So that is photolithography, and that means just we expose and develop it. So that means it previously was continuous, but depending on whether it's a positive or a negative resist, it can be dissolved or it can be hardened in places where light was. But now let's come back to the electroplating of the copper. Okay, and now we need the SAC, and the SAC is also electroplated. Okay, so here we got the SAC. Why is electroplating such a good process here?
Because it, first of all, selectively attaches onto the copper, and secondly creates those, it isotropically, so
Yep.
it creates those round shapes which are similar to plants.
Yes, there is one other point which is important. Using Faraday's law, you can determine the thickness or the amount which is deposited very well. And so you know, just by measuring your current in the electroplating, you know precisely how much tin you deposited. Okay. So, but we are not yet finished. What else is important? We must get rid of the copper and titungsten in between here, because it would short circuit our complete chip, and to that purpose, yes. To that purpose, we must modify it a little. I don't know. So, of course, also the resist must be removed here. So first we remove the resist. That has the beautiful name of stripping. So then we strip resist. Then we back etch the copper plus titungsten. And in the end, what we will still do is we remelt the bumps. For instance, in that way, that they are round balls, so we reflow or remelt the bumps. So in that way we have done the bumping, and the bumping is a very important process. So in your exam, either you take the effort to describe such bumping. You do not have to give all of the individual steps as an individual image. So if you just show me the final image and describe the steps, then it is absolutely sufficient for me. Okay. In that way, yeah, the remelting, here we should give it some let's say temperature. For instance, we do it in some hot medium, for instance, at 250 degrees centigrade, 2 minutes or so, and then we have also the conditions for this remelting. Okay, bumping is a very important process. Now let's have a look back what we wanted to achieve in our complete process. So all of the parts which we use here have been produced. So normally you could argue that can be done by external supplier, and it is, but it is assembly and packaging operations. So in that way we could say you should know. So the next two steps are flip chip soldering and assembly of the sensor element. So and here we can say the following. We have the substrate. When we go into that soldering process, we first have to use some flux or a paste on the printed wiring board. When we use a paste, we have an additional solder material. When we only use a flux, that is just in order to improve solderability, because we have seen there is sufficient of solder on the bumps already. So in fact, it's not really necessary to use a paste, but a flux is always necessary. For instance, that can be done by some spray coating or something like that. The next thing is the pick and place of the chip. And the next thing is the soldering process. There is a typical profile in temperature which I would like to see in the exam. For instance, if we say this is something like 10 minutes. So we have several temperatures. Important is, for instance, the 250 degree at which we solder. And so let's say, what do we have? We have 100, 200. So we, in some way, we heat up slowly. Here we increase a little, and then we go very fast into the soldering process, and then we cool it. And the real soldering is only in that short phase where we are above this melting temperature. So that can be something like 1 to 2 minutes at a maximum. So that would be a typical soldering process. The last thing which is important here is that could also be described in a separate step, but we can also do it here. We have an underfill. So that is important if we have our chip here. That chip is attached with the SiC, but often that is not sufficient in order to get good reliability. So often we have some additional, let's say, kind of glue we put under the chip. And that's, yeah. What's the kind of material we have for underfill? Do you have an? Yes. So, as I said, if you don't know anything about the polymer material, and it's a hardening material, of course, then typically it would be a epoxy in most cases, yes? It is also filled a little, so we have to deposit underfiller. That typically is done, for instance, with a needle dispenser. So you press it from a syringe, for instance, and then it is sucked in by capillary forces, and then you harden it. Just to have a guess, let's say 100 degree centigrade, yeah, what is it? Let's say 30 minutes or in that order of magnitude, or even only 15 minutes, but that would be a typical process. And in that way, we have an additional gluing of this chip to the substrate, and so the strength and the reliability is increased significantly. The next step would be the assembly of the MEMS. So here we deposit the adhesive. What is the next step? Pick and place chip. Harden adhesive. Could you give me some conditions for hardening? How many?
120 degrees.
Yeah. yeah, I would say 30 minutes. For instance, what would be a good idea is first do this, then we do the underfill, and so we have the hardening for the underfiller and for the chip placement in one process. That could save energy, of course, yeah? So it's not really necessary, but it could be helpful. So also the clever sequence of the processes is, in reality, it's important to save money, to be more efficient. Again, that adhesive is an epoxy. That could also be some more elastomeric material. It could be also a silicone. In that case, we would have a different hardening process than for the epoxy, of course. So that was step 7. Eight is mount in the package. So again, deposit adhesive. Here I really would use a silicone because it's softer. Pick and place. Substrate and harden. For instance, under softer conditions, okay, so it's already 1 o'clock, so we are finished for today, and we will proceed on the next Monday. Okay, do you still have questions?
I have one question.
Go ahead.
So for the mount substrate on the package, is it possible we mount the substrate first and we actually assembly the flip chip and also the sensor element, or we have to do the reverse way?
No, normally it's a good method to first to finish the substrate. So that's a traditional way. Make everything on the substrate which should be finished, except the wire bonds, because we have to wire bond anyway from the substrate to the package. That is one thing. The second thing is, for instance, what you could also do is first attach the heat sink to this injection molded frame. Yeah, so then you would have a package which already has a bottom plate, and then of course you could attach that to that bottom plate, because on the other hand you will not attach that substrate, for instance, to a PA6 bottom layer. Yes, so this package is always like a frame, and it's open. And so when you when you glue in into this frame, of course, it's not on a large area, but more on the periphery, for instance. So that could be an alternative. So you have that frame. Let me say it that way. And to that frame you would attach your copper base plate. Yeah, that could be done first. Again, we use that silicone glue here, and after that process you could mount the substrate again with such silicone, for instance. Yeah, that would be an alternative. Otherwise, what we have done is we have in some way connected that substrate to that frame here. I think maybe that here is easier. It's also depending on your equipment. For instance, if that plate is only very thin, then you can first attach it. On the other hand, when you have a very long fins, for instance, then you don't want to go into a complete assembly line with that, because typically the elevation you can tolerate over that substrate level is not very high. So it's depending. Yeah. What you could also have is some auxiliary thin layer and only then attach the substrate to it. Okay, so there are many options, let me say it that way. Did that answer your question?
Yes.
Okay, so thanks for your attention and see you. Okay.